Welcome everyone to Zahid's data mining channel once again. My name is Zahid Islam. I am a professor of computer science at Charles Sturt University, and I'm also serving as the Associate Dean Research in the Faculty of Business, Justice and Behavioral Sciences at Charles Sturt University. So today I will present one of our recent transfer learning techniques. The title of the paper is a framework for supervised heterogeneous transfer learning using dynamic distribution, adaptation, and manifold regularization. So look, I will present and introduce the paper very briefly, and it is very difficult to explain the concepts very clearly within a short time because I know you are all very busy and you all like short videos. So I will keep it short, but at least it will give you the initial understanding of the paper. And then if you go and read the paper, then that will make much better sense with the video than without the video. And also the paper comes with freely downloadable code for the technique. Let me share my screen and okay, I hope you can see my screen now. Okay, so this is our paper. The title, as I said, the paper was published with my excellent colleague, Dr. Zahid Rahman at Charles Sturt University, Australia. Now, here is the paper, the first 2 pages, and the paper was published in 2023. It's quite recent, and it was published in the IEEE Transactions on Services Computing. And, you know, IEEE Transactions on Services Computing is a core 2020 rank A-star journal, and it is also a Q1 journal in SJR. Now the paper comes with code. So let me show you my web pages. So if you search Zahid Islam online, you will eventually reach to my web page. This is the web page you can see. And then if you go to publication and search by transfer learning, it will take you to the paper. And then the full paper is available. The link is there. And you can download the paper from IEEE Explore. In case if you have problem downloading or accessing the full paper, a preprint version is also available. If you click on it, it will take you to archive, and the PDF you can download from there. And then the code is also freely available, and this is the GitHub repository of Dr. Zahid Rahman, where you can see the code. Here is the Java files. You can access the Java files. You can download them, use them, modify them, and also they will be helpful for publishing your paper. Now, that's what I'm saying in this slide. Now, the next slide shows you the preprint version on archive. Now, here is the first basic slide to explain our technique. The first thing first is transfer learning. What is transfer learning? I'm pretty sure that most of you already know, but just to quickly introduce, in transfer learning, we assume that we have a small data set. In this case, let's say this XYZ data set here. Let's imagine that this is an Australian company, let's say a travel agency, okay? And a travel agent who serves their customers, and they started collecting information about their customers and to identify whether the customer is highly satisfied, satisfied, dissatisfied, or highly dissatisfied, etc., or neutral. And the purpose of this, imagine the purpose of this organization is to collect that information to improve their business process, to identify why some customers are very satisfied and some customers are not, and then they can actually improve the customer satisfaction and their service quality. And also they can use that knowledge for future prediction, that whether this customer will be a satisfied customer or unsatisfied customer, and what they can do to improve that. And they can do it by training a decision tree. This is a decision tree. A decision tree has multiple nodes and leaves. Each node tests an attribute, and based on the attribute value, it takes the route to the next node, and then next node tests another attribute, and then based on the attribute value or value range, it then ends up with a leaf eventually. And a leaf will have records that satisfy the attribute values tested on the path from the root node to the leaf node. And therefore, each leaf will be more like a if-else statement, and we call them logic rules. So they help us to understand why some customers are satisfied and not. Imagine that if leaf 1 has 100% highly satisfied customers, and if leaf 2 has 100% highly dissatisfied customers, then we would possibly see that this attribute sales is actually causing the satisfaction versus dissatisfaction. So that's something like a decision tree. And the decision forest is an ensemble of trees. We can build multiple trees in a decision forest, and that can discover more patterns, more knowledge about the data set. Now, the problem here is, as I said, imagine this XYZ is a newly established organization, and their data collection is not big yet. So that their data set is not big yet. Maybe they have only 100 customers they have dealt with. So they have a small data set, and they are struggling to build a decision tree or a decision forest to discover useful knowledge, because the training data set size is small. And the training data set size can be small for various other reasons as well. In some domain, data collection can be extremely expensive and complicated, and time consuming as well. So they may not have large data sets, and therefore that may restrict them to build useful models, train useful models, and also discover knowledge and use that knowledge for future prediction. Here comes the transfer learning. Now, transfer learning allows you to transfer data from another domain or another source. Let's imagine that ABC is a multinational company. Maybe that can be on a different domain even. For example, it could be a health service provider, not a travel agent, but a health service provider. But they also have customer satisfaction and dissatisfaction, and the variables are, which I call attributes. The attributes are different, attribute values are different, but they have huge data, huge number of data points, records, like 10 million records. But if we could transfer that data set onto our target data set, meaning if we could project that data set onto the target data set in this form, target data set form, with similar kind of distributions and properties, then we would have a very big data set for the XYZ, the target data set for the XYZ company as well. And then they could build a useful decision forest and discover knowledge. So that is the main area of transfer learning. In transfer learning, sometimes people will build a model on the source data set and transfer the model. Sometimes people's goal will be to transfer the data from the source to the domain and then build model on the target data set, from the source to the target, not domain, sorry, and then build a model on the target data set. So in this paper, we are aiming to transfer the data, to project the target source data onto the target data, onto the target domain. So that is our goal. And so here DS means source domain and SDD means source domain dataset, and DT means target domain and TDD means target domain dataset. And we consider this is a heterogeneous transfer learning, meaning that the source domain and the target domain may have very different number of attributes and types of attributes. So values, etc., can be different. That sounds like a magic, right? But only thing we are considering that the class attribute will have some similar class values there. There can be some dissimilar values as well, but at least some values will be similar. And here in our proposed technique called TLF, we consider that we will not need to transfer all records from the source to the target. We will not transfer all records because all records may not be transferable and that may not be useful. Rather, that can cause negative transfer, causing some problem later on. So we will identify the records that are suitable for transferring and will be useful. So that is a unique property of our technique as well. Now, from the source dataset and the target dataset, we may experience distribution divergence. Distribution divergence means that marginal distributions of the attributes of the source dataset and the marginal distribution of the attributes of the target dataset may not be similar. They can be different. And the conditional distribution, the class conditional distribution of the source and the class conditional distribution of the target may also be different. So that means the dataset distribution experiences difference with the source dataset. The target dataset distribution is different from the source dataset. And then there can be feature discrepancy as well. Feature discrepancy meaning that the number of attributes can be different and the attribute types can also be different. Now, existing techniques generally handle one or the other. For example, we said that ARTL and MEDA, these two existing techniques take care of distribution divergence, but they do not take care of the feature discrepancy, whereas another existing technique, SHDA, takes care of feature discrepancy, but not so much distribution divergence. In this paper, we want to take care of all of them. And obviously, we will explain the technique in the next slide, but we use maximum mean discrepancy, MMD, to take care of marginal and conditional distribution. And then we also use manifold regularization that generally takes care of the marginal distribution side of it to maintain the manifold geometric properties of similar records before and after transfer. So similar records and their geometric properties should remain same before and after distribution, after transfer. And we also use another regularization called Ries regularization. Let us explain the main concept of our proposed technique in this slide. This figure 4 that you will see in the paper as well is a symbolic explanation of the main key concepts of the proposed technique. Okay, so let me, and this is very complex, so and you may or may not understand fully, or I may or may not be able to explain it in full clear details in very clearly, but please feel free then to read, but I'm sure that this will at least help. Okay, let us start from here, the left top left corner. So DS and DT. DS is the source dataset and DT is your target dataset. And let us imagine that these shapes represent various class values and each dot is a data point, is a record. Now the circles possibly are highly satisfied customers and the triangles are possibly highly dissatisfied customers and something like that. Okay, so you have source and the target. Let us imagine that in the source data set you have 10,000 records. each with 10 variables. So you have a matrix of 10,000 rows and 10 variables, 10 columns, and the target you have 100 records, very little, very small, and only five. And in this instance, in this example, let's say 5 attributes, 5 columns. Now, first thing first, we try to find out the source pivots and the target pivots. So what are they and how do we find the pivots? So basically the idea here is that we want to find out a set of records in the source data set that have some similarity with a set of records in the target data set. So we want to find those pivots that are connected, that have similarity. And the reason of this is that if we can identify the pivots and then the records belonging to the pivots, then possibly they are more suitable for transferring. Remember, in the previous slide, I said that in this technique, we do not intend to transfer all records of the source domain into the target domain because that may result in negative transfer. So that is why we need to find out the pivots that are the matching sets of records on the source data set and on the target data set so that they are similar somehow. Now, let me explain how we identify the pivots. So what we do here is from the source domain, we build a decision forest. I introduced what a decision tree is in the previous slide, and a decision forest is an ensemble, is a set of decision trees. Now we find the decision trees, we build the decision trees and decision forest from the source data set. So one decision tree will have lots of leaves, right? So you saw that leaves there, and then leaves will have lots of records, and those records will have class values as well, highly satisfied, dissatisfied, etc. Generally, one leaf will have, ideally, one leaf should have records belonging to one class value only, or at least predominantly a single class value, and maybe there can be some minority class values, meaning some records may have minority class values there as well. So therefore, in each leaf, there will be records, and from those records, we can find a class value distribution for each leaf. And one tree will have many leaves, and because we have a forest, we have multiple trees, so we have many, many leaves. You can think it that way, right? So here, this figure, figure 2C, shows the class distributions in each leaves of the forest. And then similar things we do for the target domain as well. We build a forest, and there also we will have many, many leaves from that forest, and each leaf will have a class value distribution, class distribution within that leaf. Now we find the leaves from the source domain forest and the leaves from the target domain forest that have similar distributions. Those two leaves having similar distribution in the source and the target will be considered as pivots. Okay, so that similarity of that distribution can be done, can be computed many ways. In this paper, we are doing it Shannon-Jensen divergence metrics to calculate the similarity of the leaves. Let's say we find a leaf in the source domain that has 100% highly satisfied clients, let's say, and we find a leaf from the forest trained on the target domain also having 100% highly satisfied clients. That means these two leaves are similar. So it tells us that somehow these records, whatever they are, kind of similar because they are highly satisfied group of people, and this in the target as well, this is the highly satisfied group of people. So these two kind of records are somehow similar. You know what I mean? So that is the concept, and that's how we find source pivots and the target pivots. So once we find the source pivots and target pivots, we then start using building a model F here, a classifier, a model, a function. And the purpose here is to build a function that will be able to classify the pivots very well. So I did not explain pivots. I explained how to find matching sets of records. But once you find matching sets of records, then for each set of record, you can find a centroid record, right? A centroid record meaning the central point of the records. Let's say a record has 10 variables, and let's say 5 of them are numerical and 5 of them are categorical. For numerical attributes, let's say a set of record has 10 records and there are 10 variables. 5 of those 10 variables are numerical and 5 of those 10 variables are categorical. Then we can find out the central record by taking the mean of each numerical attribute and mode of each categorical attribute. And that way we have a central record with 10 variables as again having those mean and mode values, right? So a pivot is the central record of the set that are matching with each other somehow. So we have these pivots. So pivot then becomes essentially like a record. So the purpose here is to find a model that will classify the pivots accurately. So what we do first is we use SRM, structural risk minimization approach. Structural risk minimization approach is something that uses functions of as polynomials of different degrees, degree 1, degree 2, degree 3, degree 4. So higher degree functions are more flexible and they can capture more differences, nuances, etc. So then the goal here is to model or train each of these functions of polynomial degree 1, 2, 3, 4, 5, etc. on the training data set and see the accuracy of those models on the validation data set. Because initially, when you increase the degree of the polynomial, it will get more and more accurate on the validation data set. But at some stage, the accuracy will start dropping due to overfitting, because when you increase the degree of the polynomial, it will perform better and better on the training data set, because it will start even catching the noise and all these things and classify even the noise. It will lose the generalization kind of thing, and that will be reflected on the validation set. So at some stage, the polynomial degree of the polynomial needs to be optimized and will be optimum. And that is the purpose of it. So we use the structural risk minimization approach to build a function f here that will be classifying the pivots most accurately here. And we also use in this equation, you can see the first component represents the structural risk minimization, which is the loss function, the prediction of WI, W being the pivot attributes, and Ri is the class of that pivot attribute. So, and we try to, basically, we are trying to minimize the loss between the predicted class and the actual class. That's the common thing for all classification model building processes as well. And the second term actually reflects the ridge regularization that we use to minimize the complexity of the model. So there will be some complexity penalty, etc., basically to avoid overfitting and to reduce the complexity. Finally, we get a model. So together, this loss minimization and ridge regularization, let's assume that we get a function, and we can see pictorially, symbolically, as I said, that this will be a symbolic representation of the main concepts of our proposed technique. We find symbolically a function, a model that can classify records reasonably well. But we can see that when they are classifying the target pivots very well, because we have trained them possibly on the target pivot, but they are not classifying all records, all pivots very accurately. So therefore, the second step in this proposed approach we do with domain adaptation and marginal domain adaptation and conditional domain adaptation, and we do that through MMD approach. MMD is the maximum mean discrepancy, and we try to minimize the maximum mean discrepancy. And that is the third component of that equation here, the f objective function, and that is the MMD of the joint distribution that we are trying to minimize. And if you expand that, we can see that joint distribution minimization involves the minimization of the marginal distribution and the minimization of the conditional distribution. So first we do marginal distribution, and then we do conditional distribution minimization. So, and then we can see that with each distribution adaptation, the function is getting better and better. So at the end of the conditional distribution adaptation, in this symbolic example, we can see that the function is actually 100% accurate. It's accurately classifying all the records. Now, one contribution that we have made here is generally in the literature, we have seen that approaches or techniques, existing techniques will take marginal distribution adaptation and conditional distribution adaptation equally importantly, but we said that sometimes it can be more important to focus on marginal distribution adaptation than conditional, and sometimes the other way around. So we used a dynamically calculated adaptive factor here that is represented by mu. If mu value is 0, then we have 100% focus on marginal distribution adaptation and 0 focus on conditional distribution adaptation, and vice versa. If mu is 1, then we have full concentration on conditional distribution adaptation, and mu can be something in between. So that we also automatically, dynamically calculate here. After we have found the function of that classifies it properly well, then we use manifold regularization, as I said before, to maintain the manifold intrinsic properties in terms of manifold geometry, in terms of the similar records before and after transfer should remain similar in terms of their geometric property, and therefore we apply manifold regularization, and then we can see the function has gotten even better. It classifies them accurately, but the classification confidence is also strong. And in this manifold approach, we also have contributed something new, which is the manifold regularization requires k nearest neighbor as a user input, k being the k nearest neighbor, that is the nearest neighbor of a record that remains similar in terms of their manifold geometric properties. Now, in the existing techniques, generally the k is a user-defined property, user-defined value, but we in this technique, in this paper, proposed an automatic k calculation. So basically, this figure here, the top right corner, explains the difference between them. So if we have a user-defined k, then we can see that these blue triangles and the void dot in the middle is the record in question, the subject record. And then if we have a user-defined k, then we capture all these records within this circle. And some of the records have actually different shapes, meaning different class values. And if a record has a different class value, like highly satisfied group, their triangles are highly satisfied group, and let's say the circles are highly dissatisfied groups, they are essentially different groups of people, right? So if we try to maintain their geometric similarity, is that the best approach or not? Similarly, for a different k value or for a different area on this red sign, we could see that we are maintaining the similarity of some records because K is user defined, but there were many more records of similar types that we are ignoring and not maintaining their geometric properties before and after transfer. So therefore, we propose a very simple approach that let us start K with 4 initially, a small number, and then increase to 5, 6, 7, 8, etc. Until and unless we see a record of the kth neighbor record having a different class value. Let's say the class value of the record in question is highly satisfied, and then K is 4. So we go to the 5th nearest neighbor, which is very similar to this record, and that's also highly satisfied. 6th, highly satisfied. 7th, highly satisfied. 8th, highly satisfied. At one stage, 10 or 11, we see now this is dissatisfied or highly dissatisfied. So we stop here. So that's our K, and we need to maintain the similarity of that K. And we tested that as well, and we saw that this red bar is the automatic K, and we use several other different user-defined K values, and we see that when we do automatic K, then our classification accuracy improves significantly. And also in all these things, in MMD and manifold regularization, we could use different kernels. Kernels are nothing but mathematical functions that generally converts data sets to a high dimensional space for comparison purposes. And there are many existing kernels, and we tested some of them, and we found that possibly cosine kernel could perform very well. But once we have got this function optimized F, then we have to optimize this function. We have minimized the MMD. We have minimized. We have also maximized the similarity of the manifold regularization step of the geometry, similarity of the manifold geometry. So we have got that those matrices settled or identified to get this most optimum objective function, right? So once we have got that, then we can use this objective function to find a alpha value here. That alpha value can help us to get the projection matrix. Remember, that is what we wanted, to get a projection matrix so that we can use that projection matrix to project the source domain dataset onto the target domain dataset. And how we get that, so alpha value, you can actually read the paper to see the nitty-gritty details of that. But basically, we use an equation where alpha can be calculated based on these values, and this M here represents the manifold regularization, and L is the Laplacian matrix for the, M represents the MMD maximum marginal distribution, and L represents the Laplacian matrix used in the manifold. So we get those values, and once we get those values, K is the kernel that can be also calculated from these values. Then we get alpha, and then once we get alpha, then we can use the source domain and target domain, multiply them to get the final projection matrix. The final projection matrix, once we get, then we can actually multiply that final projection matrix with the source domain to get the source domain dataset projected, which will be similar to the target domain dataset. Now, here is an just example. Let's say we originally had 10,000 records and 10 variables in the source domain. And then we now have 7,000 records and 10 variables. Can you tell me why 7,000 records? Why not 10,000 records? That's because, remember, we said we do not intend to transfer all records. We only intend to transfer the records that are similar, that form pivots between the source and the target. So here we got the pivots, which are the central points, and then records belonging to those pivots. So I'm just assuming that it drops from 10,000 to 7,000, something like that. So once we have 7,000 records and 10 rows and multiply by the projection matrix 10 by 5, then we get 7,000 records and 5 columns. And 5 columns, see, magic, 5 columns is the same as the 5 columns of the target data set. So now we have basically 7,000 records for the target domain. And we originally also had 100 records. So it is together, we now have 7,100 records of the target domain. Now, here is an experimental result that we also conducted to see the importance of different regularization approaches, ridge regularization, manifold regularization, and MMD, and see their impact. So we get the accuracy of our proposed technique, TLF, in terms of classification accuracy very high, but if we do sigma equals 0, meaning that we are neutralizing the ridge regularization, then accuracy drops. If we neutralize the MMD regularization, accuracy further drops. And if we also discount the manifold regularization, accuracy also drops. So it shows the importance of each of these components there. Now, in this slide, after we have in the previous slide given you the basic concepts of the proposed technique, in this slide we will quickly explain the steps that we do exactly in our algorithm to project the source domain dataset onto the target domain dataset. Now, first thing first, we build a forest and find the level distributions and centroids from both source domain and the target domain. So level distribution matrix is VS with the dimension of LS versus CS. L being the number of leaves. Remember, on the source domain, we had many decision trees, each having many leaves. Let's say we have 100 decision trees, each tree on an average having 5 leaves. So we have 5 times 100, 500 leaves. So then we basically all the trees, we boil it down to the leaf level. So we have 500 rows because 500 leaves, and CS being the number of class values, or so highly satisfied, satisfied, neutral. So let's say 5. So CS will be 5. It's 500 by 5 matrix to see the class distribution of each leaf. Then we have centroid matrix, WS, and for each leaf, there will be a centroid because each leaf contains a set of records. And if we find the central record of that, we get a centroid. So there are 500 leaves, meaning 500 centroids, and DS is the number of attributes for the source. And centroids level matrix. So each centroid will have some distribution of the class values. So that's RS, LS times 1. Oh no, in this case, not distribution, the majority class. So we are considering that each leaf has a majority class. It may have a distribution, of course, and that has been captured in the matrix VS, but RS is the majority of the class. Let's say 80% records belong to highly satisfied and 20% records are satisfied. Then in that case, the majority is highly satisfied, RS matrix. So we find similar matrices for the target domain as well. Then we remove duplicate level distributions. Imagine that because we have many leaves on the source data set, then it is possible that some of the leaves will have similar type of class value distribution. For example, one leaf might have 100% highly satisfied clients in that leaf, and it is possible that there will be another leaf also having 100% satisfied customers. So in that case, we actually merge these two leaves, and we find we merge all the records belonging to these leaves, and we find the centroid, merged centroid of this merged leaves. So that is what we are saying here, that remove duplicate level distributions and find the aggregated values of the corresponding centroids. And then we find these matrix values for source and target again. And then we find the pivots. So after we have merged, see, LS has converted to LS prime, right? Because initially we had 500 leaves. Then possibly after merging, we now have 200 leaves or 400 leaves, whatever. So that's a different number ls prime. Now with these merged merged leaves, we now compare each pair of the source and the target leaves to find out the pivots, and that we use through Jensen-Shannon divergence calculation. We find the similarity of the class distributions of the source leaves and the target leaves, and then the class distributions that are similar. In this case, we used Jensen-Shannon divergence less than 10%, meaning similar. And then we considered that these are pivots. Let's say we have NP number of pivots from the source and the target, NP number of couples in a way you can say. Now, then once we have found that, then we use them to calculate the projection matrix. This is the M, as I explained in the previous slide. We use all these pairs, and then the way I explained in the previous slide, we calculate the projection matrix. And once we find the projection matrix, it's almost the game over. We use the projection matrix to project the source dataset onto the target dataset. And then we have a bigger target dataset, 7,100 in the previous example, records in the target dataset. Then we can build a classifier like a random forest or like a CS forest, etc. Now, in the experimental section, we compared our technique TLF with 12 existing techniques and on 7 publicly available datasets, very commonly used datasets as well. And then we tested the performance of our proposed technique. Here, TLF, we can see that generally performs better. And of course, the number of records of the target dataset also matters. But for any given number of record, TLF performs better than random forest with transfer learning and random forest without transfer learning, something like that. And then once we have also tested with all 12 existing techniques, and we can see that for TLF, the best results are highlighted in bold. For TLF, we have all the bolds there, meaning for all datasets, among all techniques, TLF performs the best. And we can see that, for example, for some datasets, I'm just taking one, pi dataset, for baseline accuracy was 6.3% with plus minus 2 standard deviation. So 6.3% accuracy from if we were creating a forest, CIS4 forest, from the target domain only, then if we have so for the target domain, we consider a training data set, which is a small number of records. And from that small number of records, like 100 in the previous example, if we build a forest, then we can actually apply the forest on the testing data set on the target domain to test the classification accuracy. And that's how we did it. And 6.3% accuracy, whereas after TLF, transfer learning, that accuracy improves to 47.2%. So it's a good improvement, and we performed the best. Then we also did two interesting analysis as well. So if we consider that there are some missing values in the original data set, then we showed that we could apply our previously proposed technique called SIMI for missing value imputation. And if we do that, then our TLF with missing value imputation accuracy generally as good as the TLF had there not been any missing values in the data set. So with 10% values being missing, we can see that the TLF without the missing value imputation, considering records having missing values, if we discard those records, then we see that the accuracy suffers more than had we imputed the missing values. And of course, the percentage of missing value increases, the accuracy drifts away, accuracy slips away more, which is understandable because you have huge number of values being missing. But if we use CME, then we recover quite a lot in that sense. So that was an interesting analysis. And then we also analyzed some class imbalance data set. So for some data sets, one class value may dominate significantly. For example, 99% records are highly satisfied and only 1% records are highly dissatisfied. So then a classification model generally may come up with, regardless of anything, any attribute values, everybody is highly satisfied and the classification model can claim 99% accuracy. But sometimes that is not our goal. We want to see the people, we want to understand the people who are highly dissatisfied. So that is the class imbalance issue. And here we showed that if we build a cost-sensitive technique, cost-sensitive classification approach, like CS Forest, which we published previously in an A-star journal, Information Systems, then we generally get high accuracy along with TLF. And we have shown that TLF still performs very good, even if the data set is class imbalanced. So thank you very much for watching, and I hope that you like this presentation, very short, brief presentation. I'm sorry that the video has gone a little bit longer, but than I wanted it to be, but it will give you some good understanding of the paper. Look, the code is fully available. So now you find out flaws, and I'm sure that you are already thinking of flaws of our technique. Find out the flaws, go to the code, make changes, and see your result, run experiments and see your results, and then publish your paper. And good luck.